Hello everybody, my name is Weijie. I'm a PhD student from the Sentic Net. Today I'll be presenting a paper on AACL Findings 2024. The paper title is How Interpretable Are Reasoning Explanations from Prompting Large Language Models. So LLMs today are considered very impressive and capable of solving various tasks. Some notable examples include models such as ChatGPT and GPT-4. But nonetheless, there is an important concern regarding these models, and that is the issue of interpretability. These models are large, consisting of hundreds of billions of parameters, and are considered black box models in the sense that the receiving audience do not have a way of understanding how the outputs are derived. So one of the popular prompting techniques called chain-of-thought has emerged recently, which allows the simulating of reasoning capabilities in large language model. In the example, instead of straightforwardly prompting the model on the question to derive the answer, we show the model a few examples on how to break down the reasoning process into a series of steps so that it can do the same for the target question. The main utility is that this enhances the model's capability in solving the task and most importantly, in the field of explainability, and enables the audience to understand how the model arrives at the decision by observing the intermediate steps taken. However, there still exist questions such as the faithfulness of the explanation, where faithfulness in this case is defined as how well does the explanation reflect the model's internal decision-making process. Moreover, there may be other qualities of an explanation the user may be concerned with, which will be shown and discussed in later slides. Given the popularity of chain-of-thought, there has been multiple adaptations of chain-of-thought in recent works. Some of these are covered in the paper presented here. So for SCCOT stands for self-consistency, where instead of just producing a single reasoning path, we instead sample multiple possible reasoning paths and we pick the path that corresponds to the majority voted answer. QD stands for question decomposition, where the large language model breaks down the question into sub-questions and provide the answers to each of them before aggregating to form the final solution. These sub-questions can be seen as the model's internal reasoning process, where it first asks simpler questions and arrive at the sub-conclusions before deriving the final answer. And self-refine is a framework where the large language model iteratively refines its own reasoning process until it deems the final solution as acceptable. And lastly, we propose a new prompting approach named as Self-EntailmentAlignment, SEACOT, which is shown to improve the quality of the explanations chosen. The technique, coined as self-entailment alignment, is a continuation from self-consistency, where we have an additional step in selecting the appropriate reasoning chain. This is because in SCCOT, the concern is only on picking the best answer, and there are often times where multiple reasoning paths lead to the same answer, in which case our approach picks the optimal one based on two criteria. The first is by asking how well does the reasoning explanation entails the context. And by the context, we refer to both the question as well as the answer that it leads to. And this is intuitive, as the explanation should ideally entail the answer instead of contradicting it. For the second criteria, we chose to maximize the overlap in the set of tokens between the two contexts. So the first context would be the explanation, and the second one would be the question with the answer. And this will require an additional forward pass, where the model basically performs a self-evaluation on the different reasoning chains that lead to the same answer. So it's somewhat similar to self-refine, but instead of maximizing the alignment between the explanation and the context served. Note that it's important to note that this does not actually change the answer that it finally picks, but it only decides which explanation is best suited to explain the chosen answer. Most works that investigate the interpretability of natural language explanations usually focus on a singular axis, such as faithfulness or robustness. In this case, we instead focus on multiple axes. And most importantly, we provide a link between the interpretation metrics and the end goals that it aims to achieve. This can be seen in the words highlighted in red. In the first case, for faithfulness, you can see that if an explanation is faithful towards the answer, this can be seen as instilling trust to the end user, as the explanation does reflect the underlying process the model has taken to derive the answer. And in order to measure faithfulness, we insert perturbations into the natural language explanations in order to measure these metrics. In the first case, we insert mistakes to the explanation, where in the desired case if the explanation is faithful, the answer or the prediction should change since the explanation no longer resonates with the original answer. And in the second case, we modify the original question such that the correct label is shifted, which is termed this as counterfactual reasoning. This basically enables the detection of unfaithfulness, where the model changes its output correspondingly, but do not change its explanation to address this. So for example, a case of unfaithfulness would be if the model's explanation changes to the counterfactual answer, but the explanation does not contain the words that was edited to form the counterfactual question. For the second metric, robustness, it can be seen as a measure of confidence, such that the user can be assured that the model can reliably produce similar outputs over a range of questions that are similar. In this case, we paraphrase the explanation to see if the model's answer changes. Another under-addressed goal of explanation is how informative is the explanation, where an informative one will provide valuable insights to the audience, which may help in various ways such as providing new ideas or helping with debugging. In this case, we are interested to see when given the explanation as an additional signal to train a model to derive the answer, how much performance gain can we receive? And this is measured by using the leakage-adjusted simulability metric. Over here, we have an illustration of the various perturbation tests conducted in order to measure the 4 different metrics. So in this case, we have a question that's given to the model to produce both an explanation and an answer. In the case of both paraphrase and mistake insertion, you can see in the text that's highlighted. So for if mistakes is inserted, the ideal case would be if the model answer has changed. So from ozone to smoke. And the counterfactual scenario, we apply the changes to the question such that the correct label is changed. And for simulability, we strive to measure the performance gain by training a small model on the explanation, and we have a baseline where the model is not given the explanation to train on. And the performance gain is basically the difference in the performance. We conduct the experiments on the Llama 2 70B chat model, which have been both instruct-tuned and having RLHF perform on it. And we conduct this on 3 different reasoning benchmarks. We insert the perturbations by using GPT 3.5 and 4. And over here, we have the main figure which shows the results on the 4 different interpretability metrics, as well as the performance, which stands from the accuracy score. And we also have an aggregate score that combines the 4 interpretability metrics. And you can see over here highlighted in purple, SEA-COT outperforms on the rest of the prompting techniques on the 3 benchmarks. Over here, we have an example where SEA-COT and COT gets the correct answer. But in this case, the explanation from COT does not address the question completely, leaving the Amish cousin out of the explanation. In our case, when using our approach, it addresses both facts on the Amish shunning fashion and that their cousins thus shun them. And this may be one of the reasons as to why our approach outperforms substantially on the simulability test, since the student model is given more informative signals in order to derive or to map the input and explanation to the answer. We also conduct additional ablation studies, where we conduct the similar evaluations on smaller models such as 7B and 13B. And it's shown that larger models are capable of producing higher quality explanations. We also compare it against other ways of picking explanations when using self-consistency, such as picking a random reasoning path that leads to the same answer, the majority answer, or by picking the reasoning path with the maximum likelihood. And the result shows that maximizing both the entailment and the overlap still use the better explanation. So in conclusion, our work presents a comprehensive study where we assess multiple variants of chain-of-thought to see which approach produces the most optimal explanation. How we define this optimality is by measuring it across different interpretability metrics. And with this, I end my presentation. Thank you.